Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum cost walk in a weighted graph. The problem is marked as hard, but I would say it's not hard, but rather medium hard. The submissions are low, maybe because some of you arrived at the solution but don't know how to implement it. So in this video, we will be focusing on implementation part a bit more as well. So after discussing the solution, we will look at two different ways to implement the solution, one using just DFS and second using disjoint set union. So if you are here to watch only a specific section, all the timestamps will be there in the description down below. You can move to the section of your choice and skip the rest of the video. Having said that, if you struggle a bit during the contest, I would strongly encourage you to watch the entire video so that you get a better understanding of when to use DSU or what exactly DSU does. So with that, let's get started. The problem states that you are given an unrated weighted graph with n vertices. Now you are given an integer n and an array edges, where each edge is defined as ui, vi, wi. Note that the graph was undirected, so there is an edge between ui and vi or vi and ui with a weight of wi. Now a walk on a graph is a sequence of vertices and edges, that is v1, e1, v2, e2, v3, e3, right? Sequence vertices and then edges, vertices and then edges. So the walk starts with a vertex and end with a vertex, and each edge connects the vertex that comes before it and the vertex that comes after it. So if the sequence is v1, e1, v2, e2, this e1 should connect v1 and v2, right? Then otherwise it's not a valid walk. So the cost of a walk starting at node u and ending at node v is defined as the bitwise AND of weight of all the edges traversed during the walk, right? So if you have traversed these weights edges, the cost would simply be bitwise AND of all of them. You are given some queries where each query is defined as si, ti. For each query, you need to find the minimum cost to walk of the walk starting at vertex si and ending at vertex ti. And if there is no such walk, you have to return -1. So let's take an example. Let's say n is 5, edge is 0, 1, 7. That is, there's an edge between 0 and 1 with a weight of 7. So 0 and 1 with a weight of 7. Similarly, there's an edge of 1 between 1 and 3 with a weight of 7. Again, 1 and 3 weight of 7, and finally 1 and 2 with a weight of 1. 1 and 2 with a weight of 1. So you have to answer two queries, 0, 3 and 3, 4. That is, what is the minimum cost of a walk starting at vertex 0 and ending at vertex 3. So if you see, if you start at 0 and end at 3, this is one path, right? 0 and then this edge, then this vertex, then this edge, and then this vertex. So this is one path, and the cost of this walk would be 7 and 7, which is 7. But you can reduce this by going over 2. Why? Because the problem states that you can visit the same edge or the vertex more than once. So if you start from here, you can go to 1 via 7, then go to 2 via 1, then go back to 1 via 1, and then go back to 3. So 7 and 1 and 1 and 7. So if you take the bitwise AND of everything, you will see it will come out as 1, which is less than what you had previously. So this path or this walk is more optimal than the previous one, and you can try out any other possible combination. You will not be able to get a bitwise AND of less than 1, and hence the answer here is 1. The second query is 3, 4. You have to start at 3 and end at 4. So if you start at 3, note that you can only visit vertex that is connected through an edge. So if you want to visit 4, 4 should either be connected to 3 directly, or it should be connected to something that 3 can connect to. But neither of those are true here, and you can't reach from 3 to 4 at all, and hence the answer here is -1, right? So hope the problem statement is clear. Now how to solve this? First of all, -1 case is very obvious. If they are not connected, you will return -1, right? Now for simplicity, let's assume the graph is connected, right? And further, for simplicity, let's assume that the graph is a tree, that is, there is no cycles, right? So this is a sample tree we have, or sample connected tree we have. For illustration purpose, I have marked the nodes as A, B, C, D, E, F instead of 0, 1, 2, 3, 4. And these are the weights, and above are actually the bitwise representation or binary representation of those weights itself, right? Now let's say you have to start at here and end at here, right? So what is, because this is a tree, right, there is just one path between S and T, which is, if you follow this, this is the path between S and T, and this is the only path. There is no other path between S and T because this is a tree, right? Now if you think about it, bitwise AND of every edges you have visited in this walk would be 2. Why? Because this bit is set in all of the edges you have visited. All other bits are unset in at least one of them. So this particular bit is unset here, this bit is unset here, this bit is unset here. So all other bits are unset in some of them. So bitwise AND finally would have 0 at those bits. So overall, if you do bitwise AND, you will get a value of 2. Now can you reduce this is the question, because 2 is something you are getting, but you want the minimum bitwise AND, or you want the minimum cost. So can you reduce this? The answer depends on the fact that, is there a edge that has this bit unset, and can I visit that edge? If the answer of both of this problem is yes, then you can reduce this 2 to 0. Now in this particular scenario, there is an edge which has this particular bit as 0, and it should be visited always, right? Because we have considered that the given tree is connected, so that edge can be visited through current node. Now this edge exists on the right side of your destination. You know that there is just one path, so that path is in the left side of A, but the edge you wanted to consider is on the right side. So is it allowed? The answer is yes, because it is given that we can visit the same edge more than once. So in this particular example, one of the approaches you can take is you can start your journey, go to this edge, come back here, and then follow this route to go to the destination, right? And if you do this, you will be visiting a edge that has the second bit unset, and overall the bitwise AND would be 0, right? Now what is the, like, I hope you got the approach. So what you're doing is we are simply following up the path from S and T. Whichever bit is there which is still set, I will figure out what, if there is an edge that has this bit unset, and is that edge reachable. So second question answer is always yes, because we have assumed that the given tree is connected. So we just need to figure out whether there is an edge with that bit set, and if there is, I will visit that edge and come back, and that will be my answer, right? So what will be the time complexity of implementing this approach? Notice that the given problem has this graph. We have considered a tree, but still, what is the time complexity? What we are doing, we are going from S to T and taking the bitwise AND, so that will take you order and time, right? And after that, what you are doing, you are figuring out which bit is still set, and then you are figuring out which of the edge has that bit unset. So that will take you number of bits multiplied by log n time, assuming that you have a map or something of that sort in which you can search which edge has that bit unset efficiently, right? So overall complexity is order n plus b log n for a single source to destination, but you have q of them. So if you take all q of them, you will be requiring this many operations, right? And this is surely not passed because q and n both are 10 power 5, right? So q into n can't work. So notice that number of bits are less, right? Number of bits is only 32. So instead of going over the path from S to T, you can instead just check whether a bit is there which is unset in any of the edges, and you will visit that edge first, come back, and then visit other edge which has, let's say, second bit unset, and then come back, and so on and so forth. You will do this for all the B bits, and whatever answer you get, you will return that as an answer. Will this be a viable approach? The answer is yes, because you are actually doing the exact same thing for what you are doing when you are visiting from S to T. Let's say these are all the bits you want to unset at the end. So when you are visiting from S to T, you got some of this as 0, right? And then what you are doing, you are searching for the unset one in the other edges and see if that exists or not. So instead of doing this, why not search for this bit itself? Let's say you see, is there a edge that has this particular bit unset? If the answer is yes, from S I will go to that bit and then come back, right? So I am still at S and I am ensured that this particular bit is now 0, right? Now we'll ask the same question here. Is there a bit which has this particular, which is there an edge which has this particular bit unset? So the answer again lies in the fact that if there is one such edge which has this particular bit unset, you will go to that edge, let's say in this case this edge again. So you will go to that edge again from S and then come back. So that way you are always remaining at S, and when you do this exercise for everything, you already got what all can be unset, right? Now after this, no matter what you take, you can't unset any other things because there is no edge at all. If this is not yet unset, it means there is no edge at all which has this particular bit unset, and because that's the case, this is the minimum answer you can have, right? So this solution is also a correct one, wherein you are just iterating over all the bits, looking for which of them is unset and in the given tree, and just assuming that you go there and then come back to S. So that way your walk start from S, go to something, then come to S, then go to something, come to S, go to something and come to S, and finally you will start the walk to T, and this will not change the answer because whatever best you can have, you already have this from the first section, right? Now if you take this, then you don't need this n because you don't need to walk from S to T again. You just need the minimum cost, so you don't need the path. So that way you can save on going from S to T manually, and the complexity would become q into b log n, which will pass the given time constraint as well, because number of bits in this case is very less, because wi is 10 power 5, so it's like around 20. So 20 multiplied by log n for each query, and you have like q of them, so q into 20 into log n. So this will pass the given time constraint, but you can do better. How? notice from S you are going to something and then coming back to S, then you are going to something and then coming back to S, right? So because you are doing bitwise AND, bitwise AND is a very nice property that if a bit is unset once, it can't be set again, right? So we can take the advantage of that. Let's say if the bit is unset until here, no matter what you take, that bit can't be can't be set again, right? So with this scenario, why even let's just take one example. In this case, let's say this bit is unset. So no matter what the next number is, even if the next number has this bit set, the final bitwise AND has this particular bit unset only, right? So that's the property of bitwise AND. Now because of this property, we can avoid going over selective edges, and we can say, okay, I will just take the bitwise AND of all the edges here, because that's the best I can have. I can get the best from all these edges. That is, if a bit is unset in any of these edge, it will be unset in my final answer, right? That's what we want as well. So instead of going over selective edges using this log n and this all this iteration, you can just go over all the edges from beginning and get a bitwise and final bitwise AND. Let's call this A, and this A will be the answer for any edge or for any pair S and T which lies in this A, B, C, D, E, F. Just to reiterate, because a bit can't be set once it is unset, so why are we even bothering about going over selective edges? So what we are doing, we are first checking whether this bit is unset is any of these, and then we'll go there. Even if it is set, let's go there and let's go to all the edges, and if it is unset in any of them, this will be unset in the final bitwise AND, right? So that's basically the approach. We are going over all the edges, figuring out the bitwise AND, and that bitwise AND will be the answer for any pair of vertices between A, B, C, D, E, F, right? So hope this point is clear, that if you have a connected graph with this structure, the answer for any pair will be same. That is the bitwise AND of every edge in this graph or in this tree. Now what if this tree is not a tree, rather a graph? Let's say there are few more edges here, right? So if this tree is not a tree and a graph, will this entire thing change? The answer is again no, because what you are doing, you are just taking the bitwise AND. So you can just consider these edges as well while you are taking bitwise AND, and once you have taken these edges as well, whatever final bitwise AND you will have, that's the minimum possible bitwise AND you can achieve, and that you can achieve for any of the pairs, because you can visit any edge and any pair multiple times. So if bitwise AND is A for this entire edges, A will be the answer for any two vertices in this graph as well. So what we know if the graph is connected, the answer would always be A, which is the bitwise AND of every edges. Now let's talk about when the graph is not connected. So if the graph is not connected, let's add three more nodes in this example itself, X, Y, and Z, and these are not connected with A, B, C, D, E, F, right? So in this scenario, if you got two edges here, two vertices here, let's say X and Z, then the answer for this would be bitwise AND of every edges in this particular component, right? But if you get two edges X and C, then the answer would be -1, because there is no way you can reach C from X or vice versa, right? So the final algorithm is, first figure out the connected pieces of the graph. So this is one piece, this is one piece. For each connected pieces, figure out the bitwise AND of all the edges in that piece. Let's call it A1 here and let's call it A2 here. Now, once you have done this pre-computation, whenever you get a query of Q1 and Q2, let's say, you will figure out whether Q1 and Q2 lies in the same component. If no, let's say Q1 is C and Q2 is X. If they are not in the same component, answer is -1. But if they are in the same component, you will just go and refer to the bitwise AND of all the edges of that component. For example, if they refer to this component, that is A and C, let's say Q1 and Q2 are A and C, answer would be A1. But if they refer to this component, let's say X and Z is Q1 and Q2, then answer would be A2, right? So hope the algorithm is clear. Now, what will be the overall time complexity? What we are doing, we are figuring out the connected components. So let's assume that that can be done in order n. How I will come to that. And after you have figured out the connected components, you, for each of these component, you will be figuring out this bitwise AND of all the edges in that component. So that will take you order e time, right, for each of the component, right? So overall you will be visiting every edge exactly once for every component. Now this, once you have done this thing, for every query you are just figuring out which component does this belong to, which component does it belong to. So that you can, let's say, create a map previously as well, that X belongs to component 2, Y belongs to component 2, Z belongs to component 2, and ABCDEF belongs to component 1. So you can just do a lookup that will take you order 1 time, right? So in order 1 time, you know the component of this and the component of this. If they are same, you will return the bitwise AND of that component, that will be just order 1 as well. If they are not same, you will return -1, that is just order 1. So overall the complexity is simply V plus E plus Q, right? Now let's focus on the implementation. So assume that we have this exact same graph. Now we have renamed this vertices as 0, 1, 2 for making it similar to what the problem states. So we have this particular graph, all the edges are given, and we need to first figure out, notice the algorithm was first figure out the connected components, then the second step was to, for each component, figure out the bitwise AND of all the edges involved in that component, right? So let's focus on the first part first, and then we will come to the second one. So what we need is, for each vertex we need to figure out which component they belongs to, right? So at the end of this entire exercise, what we should have is that 0, 1, 2, 3, 0, 2, 3, 6, 7, 5 belongs to component 1, 1, 4, 8 belongs to component 2. That's what we need. So we need to fill this array such that these all will have 1 in them and these all will have 2 in them, right? So let's do small, like regular DFS, right? And because this graph can be can have cycles in them, so we need to maintain the visited array as well this time, right? So in case of doing DFS over tree, you may not need visited array, you can just need the parent node, but because this graph can have cycles, we need visited array so that we don't end up visiting the same node again and again. So let's create a copy and let's make this a visited array, right? Now everything is unvisited for now. So let's say you start at 0, right? So you make this visited. As you make this visited, let's say you maintain a array as well. You said, okay, I have discovered 0. Now from 0 you can go to 2 and 6. Let's say you go to 2. Notice we are not worrying about the edges for now, we just want the component for each of the nodes. So we go to 2. Now 2 is not visited, we saw that, so let's just make it visited, right? And also let's for making this a bit more realistic, let's add few more edges. Okay, so now you have visited 2, so let's just add 2 to our list as well. Now you are at 2, so from 2 you can visit 7 and 3. So let's visit 7 first. Let's say you visited 3 first, so we visit 3 and 3 is added to this list. Now you go to 3. Now from 3 you can visit 2. So 2 is already visited, so you will not visit it. So you will go back in your recursion state and go back to 2. So 2, from 2 now you visited 3. Now 0 and 7. Let's say 0. So 0 is already visited, so you will not visit that. Now comes 7. 7 is not visited, so let's visit that and add it to this list, right? Now we come to 7. From 7 you can go to 2, 0 and 6. So first of all 2 is already visited, so you will not visit it. 0 is already visited, so you will not visit it. 6 is not visited, so let's visit it and let's add it to our list as well, right? Now you are at 6. So from 6, 0, 7 and 5. 0 is already visited, you will not visit it. 7 is already visited, you will not visit it. Now finally you will go to 5 and visit it. So as you have visited 5 recently, add it here. Now from 5 you can go to 6, but 6 is already visited, so you will go back in the recursion and go back to 6. From 6 you have already explored all the neighbors, so you will go back to 7. 7 you have already explored all the neighbors, so you will go back to 2. 2 all the neighbors are explored, so you will go back to 0. Now from 0 you have explored 2, so let's explore 7 now, but 7 is already visited, so you will not go to 7. Now 6 is already visited, so you will not go to 6. So your DFS will end here. Now at the end of this DFS, what you will have is you have marked some of those nodes as visited, and which of these nodes you have marked is in this array. So basically all these nodes are part of one component, right? So what you can do, you can now iterate over all of these and assign them one single ID. So let's say you assign them 1. So 0 is 1, 2 is 1, 3 is 1, 7 and 6 are 1, and finally 5 is also 1. So all of these are 1, that means they all belong to the component whose ID is 1, right? Now you will go to 1 and start exploring because 1 is not yet visited. So same thing, you will now maintain a new list because that will be part of a new component. So you added 1 here, mark the 1 as visited, explore the neighbors. So 1 to 8, let's say. So 8 is not yet visited, so we'll add 8 to your list and mark it as well. Now from 8 you will go to 1, but 1 is already visited, so you will go back in the recursion state and you will reach back to 1. So 1 you have explored 8, now you will explore 4. So 4 is not yet visited, so you will visit it and also add it to your list. So you will go back to 4. From 4 you want to go back to 1, but 1 is already visited, so you will not go back to 1 and go back in the recursion, and finally 1 has all the neighbors explored, so recursion will end here. So again you have visited these 3 nodes in the current recursion, and it means these 3 nodes are a part of a one component. So 1, 8 and 4 are part of one component, right? So let's mark it to a new ID. So what we have now is the component for each of them. So if there is a query Q1 and Q2, you can simply look up Q1 here and look up Q2 here. If they are not in the same component, you can return -1, right? But if they are in the same component, let's say Q1 is 2 and Q2 is 6. So if they are in the same component, then you need to return the bitwise AND of all the edges of that component, right? So how to do, like, we have to figure out that as well. So now we have 2 components, 1 and 2, right? We need to figure out what is the bitwise AND of all the edges of component 1 and bitwise AND of all the edges of component 2, right? So one way could be go over component 1 again and see the bitwise AND of all the edges. That is doable. And second way could be, let's not worry about the component by component, let's go over all the edges, and if they I am sure that this edges will connect two vertices that belongs to same component. So let's initialize this with int max, right? And now whenever you see an edge 2 and 7, we are sure that 2 and 7 should belong to same component because they are connected. So 2 and 7 is actually belonging to the same component, right? That should be there. So we will simply do whatever was there previously in that component and AND it with the current value. So m and 15, and if you do this AND, you will get 15, right? So this edge is done. Now this edge, let's say 8, 2 and 3, 2 and 3 belongs to the same component, that is 1. So you will again go back to 1 and AND it with 8. So if you do this AND, this will be 8. Now let's say you got this edge. You are iterating randomly, right? So you can get any of them. So you got this edge. So this edge connects two vertices 1 and 8. 1 and 8 belongs to component 2. So now you will go to component 2 and do max and 8. And if you do this, it will be coming as 8. Now let's say you got this 7. Again the same thing, 6 and 5 belongs to the same component 1. So you will simply go here and do a 7 and this will this will yield 0 here, right? And you will do the same, you'll keep on doing this for all the edges, and finally you will have the bitwise AND of all the edges here, right? And once you have this bitwise AND, you know the answer for every pair, for even for pairs for which the components are same. You will simply look up here and get return the answer. Let's say you get 2 and 5, the component are same, so you will simply go to that component ID and return that as the answer. If component are not same, you will return -1, right? So that's how you will implement this entire thing with a single DFS, and overall complexity is simply order n plus e, right? Plus q as well, because you are answering q queries as well. So now let's look at how you can implement this entire thing using disjoint set union. So what disjoint set union gives us is this array out of the box. So if you know disjoint set union algorithm, you don't need to iterate over this components one by one and create these vectors and then mark their IDs. Disjoint set union gives you this array out of the box, and once you get this array, rest of the things is exactly similar. So once you get this array, you will now iterate over each of these edges and build this array, that is what is the bitwise AND of all the edges in a single component. And after that, for answering, you will follow the exact same algorithm, right? So if you know bitwise disjoint set union, you can simply apply DSU and you will get a leader for each of these nodes, and this leader is equivalent to ID for each of these nodes itself, right? So let's look at the code for the disjoint set union part, and I would encourage you to code this DFS approach by yourself, because that is something which is very common and you should be able to implement it by yourself. So would strongly encourage you to pause and try to implement the DFS approach by yourself, and if you do disjoint set union, obviously code that as well. Next, we'll be looking at the code for the disjoint set union, and I will attach the DFS code in the description if you want to refer. So what we are doing, we simply create a DSU struct, and for each of the edges we just merge their vertices. Though after this 2 lines we will have this array, right? And once we have this array, what we are doing, we were iterating over each of these edge and then doing a AND for that component. So that's what we will do for each of these edge. We will figure out their leaders, and we are sure that they should be the same because they are connected, so they belong to the same component. Now we will simply do AND for each of them. So either you can have it int max here, that will work, or I have done -1 here. So if it's -1, I will just assign it to e2, otherwise I will do a bitwise AND. the same thing. So after this thing, we will have the bitwise AND for all the leaders or all the components. So we'll have this array built. So we'll iterate over all the query. For each query, this is edge case. I would leave it to you how why this edge case is there, but let's forget about that for a moment. We will figure out the leader for x and y looking at this array or asking DSU, that's fine. And if they are not equal, answer is -1. If they are equal, we will simply look at the leader value and return that as an answer, right? Now finally, DSU code is the standard one. We simply initialize the parent array and the size array. Size is 1 because each of this component, each of the node is its own component. So in the initial state, this is one component, this is one component, this is one component, this is one component, and so on and so forth. So each of these node is a single component of its own, and they are the leader of its own. So if you figure out what is the leader of 3, leader of 3 is 3 because that's the boss of this particular component, right? So we initialize the component size as 1 and the leader of everything is them itself. Now when you merge, you figure out the leaders first. If they are same, then they are already merged. If they are not same, we will merge the larger one into the smaller one. Sorry, we'll merge the smaller one into the larger one. So and reset the parent of the smaller one. And the leader algorithm is simply, we are doing, if x is equals to px, then that's the leader. Otherwise we'll figure out the leader of the px, and that will be the leader for x as well, right? So this is the standard DSU algorithm. Hope this entire solution is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.